Hello, everyone. It's great to see my co-authors, colleagues, and friends in this room. Yes, I'm super happy that you come here to support me, and so that I'm not alone in giving the talk. So today I will talk about some problems of using ciphers and hashes in zero knowledge. Well, the problems, they don't specific to zero knowledge, but people who work in ZK, they face them. Sometimes they face them without noticing that they face them. And I think it's important to draw attention to this at some points. Feel free to interrupt me with questions and walkovers. So it's totally fine. OK, so we all know that there is a lot of cryptography in projects we are working on. And most of this cryptography is what people call public key crypto or protocols. And I will be talking today about symmetric crypto. Symmetric crypto is actually not that popular, but still it constitutes a good portion of hash functions, VDFs, and encryption. So we may think that in public blockchains, like, for example, Ethereum and others, we don't have a lot of encryption. But in fact, we do. We do use it on the client side to store secrets, to encrypt the storage, to derive secret keys, and also occasionally in applications. So many applications, even when the data is transmitted to blockchains, there are sometimes use cases when the data is not for everyone, but for certain people, like, for example, in Zcash, when you transfer money, transfer coins from one person to another, the recipient must know some content of the coin. This content is encrypted. And actually, that's one of use cases. And since we use encryption, we have to know how to use it and what are the most popular problems here. So symmetric crypto is commonly known as the place where the secret key, if it exists, is just known to all the parties. Well, when you are not an adversary, it's known to you. So pretty much the same person who encrypts, the same person decrypts, or they both know, if there are different people, they both know the secret key. And examples are blocks and stream ciphers, hash functions, message authentication code, and certain kind of signatures. And there are many names here that you have seen in different contexts, from AES to Sphinx. They all belong to symmetric cryptography. Interesting thing that theorists and practitioners, they've used symmetric cryptography very differently. So for actual users and developers, symmetric crypto is something that is really fast, and this hasn't changed much since you started developing, because many like AES and SHA libraries are around in, say, in OpenSSL for decades, really. However, for cryptographers who got used to rigorous definitions, formal reductions, and proofs, this is something like kind of vaguely defined, some really elusive thing that you try to attack it, and then you figure out you can't really attack because that's nowhere defined what you have exactly to attack. So many names, things get broken and unbroken every year. So many designs are like mess of something, and you don't understand why is this mess all around. These views are very different, and they, of course, both are true as we have us in our real world. OK, so let me start with ciphers first, because ciphers are often overlooked. So we often promote our new hash functions, for example, but ciphers are very interesting beasts, and I think I would like to draw even more attention to them in this talk. So ciphers, basically, whenever you need encryption, you need a cipher. You want to protect from something when you encrypt. And there is nevertheless not always easy to define what exactly you protect, and from what you protected, from what kind of attack you protected, what is an attack in your context, what is not. Every time you feel there is some asset that needs protection in symmetric case, you have to answer several questions, like apart from the asset you protect, but also what are the performance requirements you have to satisfy. Because sometimes the application is so requiring that you're not able to find a really good solution, or the good solution that you have doesn't satisfy the requirements. Sometimes you are restricted in the language, in the set of libraries, and in the maturity maybe of a design. Oh well, I definitely should have waited more. Okay, I'll have a short pause. Yes. Okay, for those who have just come, a short recap of previous episodes. So we have been talking about symmetric cryptography, that in symmetric crypto we have ciphers and hash functions, and sometimes VDFs, but VDFs we will not be talking about. And I've just started to talking about why we need encryption, and in case you do need encryption, which questions you have to answer first before you actually do start encrypting something, or even start selecting your primitive. So you have many questions, and I would like now to highlight some important difference between the user experience of encryption and what's actually happening when you try to encrypt something, what should happen in the correct library. So how we want to see it, we want a very simple API with just two functions, encrypt and decrypt, which may fail, of course, occasionally, but in general, we don't want nothing more than that. But whenever you encrypt, what should happen? First of all, there must be a secret key somewhere. This secret key must persist. It's not usually some one-time key, but it's a key that must be generated from somewhere, and must be stored somewhere. It should be retreated from there. Second, many encryption schemes, they need either randomness to start, or they need kind of a nonce or a counter. So they're kind of stateful. They're stateful between encryptions. So there is some state you have to inherit from a previous encryption session. This is something that you have to not only store, you have to retrieve it securely. You have to check that, for example, if there is nonce, the very much definition of nonce is that something that you used once. You have to care that you use it once. You have to update it after you use it. You have to be 100% sure that you never use the same nonce twice, because otherwise you may break the security of your encryption thing totally. So sometimes repeating a nonce is almost as bad as leaking a key. The thing is, this nonce is not always obvious. So sometimes you can generate it randomly, but for many reasons, some libraries don't generate it randomly. When it's not generated randomly, and there's a counter, you have to make sure that the counter is updated right. After you have done your dirty thing, you have to zeroize every memory segment, because there can be some remnants of the secret key, there can be some remnants of the state during the encryption, and so on and so forth. That's actually very non-trivial. So that's probably the deal of low-level developers. But up until recently, it was not trivial even in the C language to guaranteedly erase an array of data, because compilers nowadays are super smart, and whenever they see you fill something with zeros, they badly want to optimize it, because it's clear that you don't need this data anymore. Okay, let's go into the security properties you have to take care about. So the very simple thing that you need from encryption is that you have to preserve confidentiality. So the one way to define confidentiality is something that informally, if you don't know a key, then you can't say anything about the message. When you look into the ciphertext, then any message can be could be a plain text if you don't know the key. Or if you rephrase it in a more formal way, then whenever you encrypt two different messages, then the ciphertext are, and you are given only one of encryptions, then the cipher you can't figure out what was encrypted of the two. This actually is not sufficient for most of use cases of encryption, because to preserve confidentiality is one thing, but to decrypt back is another. In the simplest modes of operation for ciphers, when you just encrypt something without an additional guarantee, it may be possible that an adversary just simply changes whoever is able to tamper with the ciphertext. If there is no extra protection, then basically you can just flip a bit. It may happen that in the result in plain text, just a single bit will be flipped, because in the most optimized cipher, that's actually what happens, that the diffusion between plain text and ciphertext is very small, and it may happen that a simple kind of fault attack on the ciphertext will result in a very small change in plain text. What you need, if you do care about the so-called integrity of the plain text or of the ciphertext, that you need that whenever something new ciphertext is produced, something that was not a result in encryption, then it must not decrypt, or it decrypts to garbage whatever you decide. So altogether, these properties are called authenticated encryption, and this must be a default option whenever you use a cipher in the ZK context or any other context. So there is very, very little, very small area of use cases when pure confidentiality is enough. But instead, you should aim for authenticate encryption. And authenticate encryption is missing in a popular mode of operation, like a counter mode, for example. So you shouldn't aim for a counter mode, but you should aim for some more advanced version of encryption. So whenever you implement authenticate encryption, there are problems that developers of popular encryption libraries like OpenSSL, they have come over in the last decade. But since we are in the environment, and like in the ZK environment, when new libraries appear, because we switch to new languages, we like Solidity or Rust or something, and we write pretty much the same functionality, but in a new way, we sometimes forget the lessons that of the past. And one rule, for example, when you decrypt something, since you may work with a very large amount of data, when you decrypt a large amount of data, you know that if there is a kind of a tamper, if the data has been tampered with, that eventually it should decrypt to an error. But when you start decrypting it, it may be okay, like you decrypt 1 kilobyte, it's okay, decrypt second kilobyte is okay, megabyte, gigabyte. In the end, there will be an error. But what you have done in the first, with the first megabyte, you should not release this data to the user. So your intermediate state, you should never release until you finish your decryption in full and figure out if there is an error or not. Because there are some very subtle attacks when software releases the kind of intermediate results of decryption. Because, well, basically, informally, the chaining between the parts of the data is not diffusive enough to protect us from certain kinds of attacks. There are other interesting properties like, for example, key commitment. But fortunately for the ZK environments, this is not very kind of common. So the thing is, if a ciphertext can be decrypted onto two different keys, in certain use cases it can be a problem. There were like practical attacks on password recovery whenever it was possible in the software to be decryptable by two different keys. Certain schemes prohibit this kind of functionality, but certain ones allow. Whenever you implement an encryption for your protocol, you have to think whether this so-called key commitment property is a property you have to fulfill. If so, you have to be triple care about selecting a right cipher seed. Okay, so one more interesting point I would like to highlight here in the context of ciphers is that there is a very long distance actually from the cipher itself, how we know it. For example, if any of you have looked into how AES looks like and how it looks in so-called mode of operation. There are very many modes of operation developed over years, starting with CBC and CTR, which are discarded nowadays for good reason, because they are confidentiality only and prone to certain kinds of attacks. GCM is something more secure, but you need care with nonces. There is a mode built on top of GCM which doesn't need nonce, but it still requires, well, basically it's SIV, it's called synthetic IV, kind of a synthetic nonce, and it derives its synthetic from actually the data that it encrypts. So you shouldn't encrypt the same data twice, because otherwise this will be seen. But if you don't, then it's perfectly fine and can free you from nonce handling. This is a nice picture I like to show. It demonstrates the mode of AES GCM. And you see AES itself is this EK. And all this mess around it, what constitutes this modes of operation. So this mode of operation is not just split the data into chunks, encrypt this with that and this with that. No, you see there are like XORs, multiplication in the Galois field, some encryptions of zeros out of nowhere, and so on. Some truncations you see, like here you have to encrypt, but then you have to truncate this small portion of a 128-bit block. That's like really super crazy. And all these modes are, well, I wouldn't say they are error-prone, but mistakes are being found, and there are proofs like decades after these things were introduced. So thankfully, these things come now with security proofs, and in these security proofs, people do find bugs. So that's how we... Okay, and now I give a simple example. That's what I mentioned in the very beginning, that there is a private mixer or some private cryptocurrency, and if there is a task to send one coin to another, then how basically you answer the questions that I've mentioned in the very beginning. So you have to figure out what you have to protect, like the blinder or a secret, however you call it, and the coin, the amount. And then you figure out, okay, so I protect the amount and the secret. Do I care about confidentiality? Yes, I do care. Do I care about integrity? So what happens if someone changes the ciphertext on its way to blockchain? Is it really bad? Well, I would say it's rather bad, because this means that the recipient will not be able to decrypt the ciphertext, or it will decrypt the garbage, and this means that the recipient will not be able to spend the coin which you sent to them. So integrity must be protected. So it must not be just simple AES in the counter mode, but something more sophisticated. Apart from that, you can select some nice cipher, but then, for example, if you want to prove that you have encrypted the necessary data to the recipient, and you want to prove it in zero knowledge, so that you don't intentionally produce garbage in ciphertext, then it means that a cipher you use must be somehow ZK friendly if you care about prover performance here. So you have to select some cipher that is more or less ZK friendly. You don't have actually big number of options there. So AES is not particularly ZK friendly. It's kind of okay. Maybe it's even okay for your protocol. Depends how faster your prover has to be. An alternative is to use a sponge hash in a duplex mode. And this is a reasonable way, but there must be some care again how to call this sponge in a duplex mode. Okay, here's a nice table about encryption problems that may appear in the cryptographic part, like in the research part of a cipher and in implementation. and there can be numbers of them. I think I would rather skip this table and go to hash functions, because I don't have that much time left. Hash functions are multi-tool. And you see they used in compressions, for commitments, sometimes for encryption. The security of hash functions is somewhat easier to formulate. Basically, we need three things from hash functions. We need them to be one-way or pre-image resistant. We need them to be collision resistant. We need them to be uniform, meaning producing uniform outputs on unknown inputs. All these three properties, they don't follow from each other. So I like showing this counterexamples. For example, if you use an identity function as a hash, then it's collision resistant because, well, it doesn't compress, so clearly no collisions there, but clearly not pre-image resistant. If you take a secure hash function and prepend the 0, it's collision resistant and it's pre-image resistant, but it's not uniform. If you take your input and truncate part of the input and hash the rest, it's still pre-image resistant if the rest of the input is big enough, but not collision resistant clearly because it ignores the first part and uniform enough. So you have to think, for example, sometimes it's tempting to drop a few bits from an output of the hash function, basically meaning that you zeroize them. The question is, do you need your hash function to be uniform enough? Sometimes you don't, sometimes you do. So depending on answer to this question, you have to use all the bits you have or not. Hash functions are always difficult to choose. You can't just make them fast, secure, and convenient and well-tested. You have to choose from some things, and new hash functions are always in development. There will be a talk by a colleague of mine, by Roman, in an hour. Who will be talking about another design. So it will be super fast and super new. So for some of us, new is not really good because we want to be conservative. It's always good to be conservative, but it's also fun to create something new. So it's a difficult dilemma or even trilemma here. Okay, there are a number of problems in hash functions. In old hash functions, there is so-called length extension property. But length extension property is something, how we call it. Basically, if you have a guy with very short hair, is it really easy to get from there to a guy with a long hair, like a really powerful guy, and do it for free without doing any effort? So in some hash functions like SHA-256, this is possible because what they do, when you hash two long messages together, a concatenation of two messages, it's something like you first process the first message and then you hash into the second message. And what it means is that if the first message is some kind of a key, then you can produce like key-dependent hash without even knowing the key if you simply extend the first message with some suffix. So I think I actually gonna skip this stuff. So some nice hashing bugs that are very, very well known to many of us is whenever you use the same hash function in different contexts, but in the same protocol, you immediately get problems with security proofs, and you may have collisions. And these collisions, they're not something like really breaking your protocol, but they may forbid you from finalizing the security proof of your protocol. So basically, whenever you have multiple random oracles in the same protocol, you must not instantiate them with the same hash function, but you must, in reality, you have maybe one hash function or two hash functions. So there must be a way to separate them, use some kind of a domain separation. And there must be a library that does this domain separation properly. That must be a way to produce all these domain separations. And that's way how many you need. When you hash multiple inputs, you have to concatenate them properly because most of our hash functions, they take just one input. If you use like multiple inputs, you must provide a way to hash function to distinguish between like one long input and concatenation of different inputs, so like just different inputs. So there must be some injective function that does this kind of packing of inputs. And finally, one nice thing is about what if the hash function works in one domain and you wanted to output your number in another domain. So to this I devote there is a very simple set of rules actually. What happens if you output from ZP and you need elements of ZQ? Well, P and Q don't have to be primes here, they're just different. Sometimes it's enough to take a modulus, sometimes it's not enough to take a modulus, sometimes you have to concatenate the inputs and sometimes not. But there are actually very simple rules and they depend on how P and Q relate to each other. So you can go to our hackmd and check how it's done. There is another misuse that is nowadays popular, that when you use a sponge function, sometimes you work with the so-called capacity part and you initialize it with simple constants. And the thing is, you should not initialize them with simple constants because it's possible they collide for different use cases and you can't really make security proof out of it. So the safe API that Michele has just recently covered a little bit provides this kind of protection. Yes, so, well, we have talked already about safe API in the previous calls, in the previous talks, so I will not concentrate about this too much, but the idea is that basically you can have all the applications of a hash function inside one library that does all this domain separation, padding, encoding, decoding, and so on, field conversions out of the box. Okay, so please encrypt, decrypt, and hash safely. This is the way.
Thank you very much, Dmitry. We do have time for maybe one or two questions, so raise your hand if you have any. Okay.
Actually, I had two, but I would just choose one then. You talked about AES GCM.
Yep.
And what was the issue with SIV? I mean, you said, can you repeat the issue that you mentioned with ESIV mode of operation?
Well, I said that there's a GCM CIF mode that basically it's SIV stands for synthetic IV, so it generates as IV, but it generates it's using the data itself that's to be encrypted. So it doesn't use internal randomness and doesn't work with the nonce.
The synthetic IV uses the nonce and the message. So the problem is usually if you reuse the nonce, then you know you have encrypted twice the same message.
Yes.
But if you choose a different nonce every time, it's fine actually.
Well, if you additionally use a nonce, then yes. Well, but if you already have a nonce, you don't have to use SIV. You can use just regular GCM. This is more about the case when you don't have a nonce, but you have some way to guarantee that messages are unique.
Okay, then in that case, okay. So we'll skip the second question. I'll ask you offline.
Okay.
Just the last one, because you raised your hand very quickly, and then we'll be done.
So you talked about different bugs for encryption, but you haven't talked about padding at all, which is quite important because there's been TLS Poodle, there's been the Blasian Basha attack, well, 1 million cipher attack. So I'm not really sure if there's any new recommendations about padding.
Yes. So actually, our basic recommendation about padding, in particular when you are in ZK, is to use Safe API, because it cares of the padding in a simple way. Basically, we cover all the use cases when the length is known at runtime. And when the length is known at runtime, simply kind of what we do informally, we just hash it into the capacity part of the sponge. And this makes the state dependent on the length. So you just can't use it with different lengths. It doesn't decrypt, and different message of different lengths produce you different outputs. If you encrypt, produce you different encryptions. So basically, when you know it at runtime, and when you basically, or in terms of a cipher, the IV depends on the length. We just hash it into, and this takes care of these attacks. We think is actually simpler than to introduce special padding schemes because they are all fairly complicated. Yes.
Is there time for one more? One more?
Yeah.
You talked a lot about Sponge. So what's your opinion on, it's quite old and maybe you will say that we should never use it, but on the use of compression function and Merkle-Dam guards. It was really popular 8 years ago, something like this.
Well, yes, because, many modern hash functions, even like Blake, it uses some sort of a Merkle-Dam guard. So there are some precautions you make there to prevent all this length extension problems and so on, but by certain use of counter, you can work with it. It's good for kind of incremental hashing, but it's not that nice when you use different hash functions in your protocol in many contexts. Like here's a hash function for commitments, here's a hash function for hash function, here's a hash function for encryption, and so on. So, and here like earlier boards when you do fiat Shamir. So we think that the Sponge interface and based on that, the Safe API provides you actually the better. It's somewhat more flexible and less error prone than when you use Merkle-Dam guard. But you can plug the Merkle-Dam guard hashes into the Safe API. So Michele has this code that does that. There are some other constructions that do that. So you do.
Pretty much a copy of leaf signal stuff. So giving credit.
Yeah. Okay. So. If you have old hash functions, it's still possible to use them in the new API. So there is compatibility there.
Thank you.
Perfect. Thank you very much, guys. Now it's time for a break. So we'll be back here with our next speaker at noon. So yeah, see you there. Thanks, Dmitry.